Hello and welcome to another Toyota Technical Training Program.
That engine starting and those lights coming on can be most reassuring. Yet today's Toyotas are among the most reliable vehicles in the world, thanks in part to an increasingly sophisticated electrical system. And without a doubt, that electrical system is becoming increasingly sophisticated. Cranking the engine and lighting the lamps are just two basic uses of electricity on Toyotas. Other, more advanced uses of electricity on the vehicle include those for added comfort, for increased convenience, for improved safety, and for superior performance. In fact, today's Toyotas simply wouldn't be the same without electricity. And that's why today's service technicians must become more knowledgeable of the vehicle's electrical systems, how they work, how to diagnose problems, and how to correct the causes of those problems. In this program, we'll focus our attention on the battery, the primary source of electrical energy on Toyota vehicles. Our look at the battery will be a thorough one. You'll learn about the battery's function, or what it does, construction, or how it's built, operation, or how it works, diagnosis and testing, or how to identify causes of problems, and service, or how to correct those problems. Let's begin then with the battery's function, or what it does. Using an electrochemical reaction, the battery changes chemical energy into electrical energy for starting, ignition, charging, lighting, and accessories. We often hear that a battery is good or bad, but just what is a good battery? A good battery delivers electricity when needed. It accepts electricity to maintain a proper state of charge, and it acts as a voltage stabilizer for the vehicle's entire electrical system. When the engine is not running, the battery is the vehicle's only source of electrical energy. If needed, electricity from the battery can be used to operate the lights and certain accessories. When the engine is being started, the battery is again the source. Battery electricity is used to energize the starting system, as well as the ignition system. When the engine is running, the battery gets some help from the charging system. Battery electricity energizes the alternator, which in turn generates electricity. At low speeds with the lights on, the battery and charging system work together. But at high speeds, the charging system supplies all the current needed by the vehicle's various systems. Once those needs are taken care of, it then sends current into the battery to restore its charge and prepare it for the next time its power is needed to start the engine. And last, but no less important, the battery also functions as a voltage stabilizer, or large filter in the vehicle's electrical system. It smooths out or reduces voltage surges that might otherwise damage certain electrical or electronic components. Next, let's look at battery construction, or how it's built. The battery is often thought of as a storage tank for electricity. That's not really true. Instead, the vehicle's storage battery holds chemicals which can produce electricity. These chemicals are stored in cells or small compartments inside the battery. Here's a very simple cell. Two different pieces of metal suspended in a liquid chemical. One metal has a positive electrical charge, the other a negative electrical charge. If you connect a conductor and a lamp between the two metals, the chemical reacts with the metals and current will flow to light the lamp. But when most of the chemical and metal have reacted, the cell won't be able to produce any more electricity. This is called a wet cell, and its biggest advantage is that it can be recharged by sending current back into it in the reverse direction. The chemical reaction is reversed, and the liquid chemical and two metals can be restored almost to their original condition. The positive material is made of brown-colored lead peroxide. The negative material is made of gray-colored sponge lead. The chemical is a mixture of water and sulfuric acid called electrolyte. This electrolyte reacts with the positive and negative materials to produce electricity. In such batteries, active material is bonded to a conductive metal grid to make a large plate. Several plates are then welded together with a plate strap to form a plate group. The plate strap has a terminal for making electrical connections. The number and size of the plates determine current capacity. Batteries with large plates or many plates produce more current than batteries with small plates or few plates. Each cell has one positive plate group and one negative plate group. The positive and negative plates are alternated. Separators act as electrical insulation to keep the plates apart, yet they are porous to allow passage of electrolyte between the plates. The complete assembly is called a cell element. It includes two plate groups, one positive and one negative, the separators, the connecting straps, and two terminals. The cell element is placed in a case containing the electrolyte. When the electrolyte reacts with the plates, about 2.2 volts of electricity are produced. No matter how large or how small the cell is, it cannot produce any more than 2.2 volts. So to get more, cells are connected in series. The number of cells determines battery voltage. Toyota vehicles use what are called 12-volt batteries. To get about 12 volts, 6 cells are connected in series using cell connectors. Since each cell is capable of producing about 2.2 volts, this size of battery can provide about 13.2 volts. Because of some internal resistance, however, such batteries are considered fully charged when they can provide about 12.6 volts. So now that you know what a battery does and how it's built, let's talk about battery operation, or how it works. We'll discuss what happens during the battery's discharge-charge cycle, why certain factors reduce the battery charge rate, and what battery capacity ratings mean. The discharge-charge cycle describes the battery's chemical condition when it's fully charged, discharging, fully discharged, and charging. In normal use, of course, the battery is not allowed to become fully discharged before charging begins. But even with this, the battery's life is limited because each cycle will cause some dilution of the electrolyte and some sulfation of the plates. In a fully charged battery, the electrolyte is at full strength with maximum sulfuric acid and minimum water. The positive plate is lead peroxide. The negative plate, sponge lead. These active materials cannot react until the circuit between the battery terminals is completed. When a load is connected to the battery terminals, current begins flowing as the electrolyte reacts with the plates. This chemical reaction forms lead sulfate on the positive and negative plates and dilutes the electrolyte by changing some of the acid into water. This is called battery discharging. The plates gradually become chemically similar and begin to lose their different electrical charges. A discharged battery has very weak or diluted electrolyte because most of the acid has changed to water. Both plates are sulfated, mostly covered with lead sulfate. The battery now stops functioning because the plates are basically two similar metals in the presence of water. During charging, the chemical action is reversed. The lead sulfate on the plates is gradually dissolved, changing the negative plate back to sponge lead and the positive plate to lead peroxide. The sulfate is dissolved in the water. This increases the sulfuric acid content and returns the electrolyte to full strength. The battery is automatically charged by the vehicle's charging system when the engine is running. It can also be charged by a battery charger when the engine is not running. Several factors, however, affect the charge rate. The charging voltage must overcome the battery's CEMF, or counter-electromotive force, the amount of voltage produced by chemical means in the battery. And it must also overcome the battery's internal resistance, the amount of resistance in terminals, connectors, straps, and plates. Both of these are affected by temperature, state of charge, plate area, electrolyte impurities, and gassing. Battery temperature has a significant effect on the charge rate. It thickens or thins the electrolyte to increase or decrease its resistance. A cold battery will be difficult to charge, and a warm battery easy to charge. The battery's state of charge also affects the charge rate. A severely discharged battery with sulfated plates will take longer to charge, or it may not take a charge at all. Plate area is also important. Large plates take longer to charge than small plates. Electrolyte impurities, such as washed-off plate material or dirt, add resistance to current flow. Charging takes longer, and some plates may be shorted out. And last, gassing. Gassing occurs during charging, and it too affects the charge rate. Hydrogen gas bubbles form at the negative plates, and oxygen gas bubbles form at the positive plates. These gases limit the chemical reaction at the plates, and when they bubble out of the electrolyte, they wash active material off the plates. Once charged, the battery should be able to provide adequate power. However, the battery must be the right one for the vehicle. It must fit and have enough capacity to do the job. The various capacity ratings include cold cranking amps, reserve capacity, power, and amp hour. The cold cranking amps, or CCA rating, indicates the power a battery can supply for engine cranking under low temperature conditions. Toyota batteries have CCA ratings ranging from 350 to 560 amps. The reserve capacity, or RC rating, indicates how long a battery can provide sufficient emergency power if the charging system fails. Toyota batteries have RC ratings ranging from 55 to 115 minutes. The power rating indicates a battery's cranking power in watts. Toyota batteries have power ratings ranging from 2,000 to 4,000 watts. The amp hour rating indicates a battery's lasting power under light load conditions. Toyota batteries have amp hour ratings ranging from 40 to 80 amp hours. Besides these electrical ratings, Toyota replacement batteries are also rated for either 24, 36, or 48 months of service. These give the customer a choice of cost and expected service life. When replacing a battery, however, make sure you check the electrical specs. The replacement battery should have a capacity rating that is the same or better than that of the original. With that, you know how the battery should work. So let's turn our attention to diagnosis and testing, or how to identify causes of problems. All batteries have a limited life, but some conditions can shorten that life. These conditions or causes of battery problems include low or diluted electrolyte, corrosion on terminals, overcharging, undercharging, cycling from fully charged to fully discharged and back many times, both high and low temperatures, and vibration. These causes of battery problems can be easily identified. Physical problems can be found in a thorough visual inspection. The battery's chemical condition can be measured in a state of charge test, and the battery's electrical condition can be checked by a heavy load test and a 3-minute charge test. When checking or testing the battery, always make safety first your biggest concern. The dangers of gassing are especially important to remember. Gassing may form an explosive vapor near the battery, even though the vent caps help to minimize this danger. Any spark or flame can ignite the gas and turn the battery into a potential bomb, a very powerful bomb. Thousands are injured each year by exploding batteries caused by carelessness. Also, keep in mind that the electrolyte contains sulfuric acid, a very corrosive chemical. It can eat your clothes, it can burn your skin, it can cause blindness if it gets into your eyes. If you ever get electrolyte on your skin or in your eyes, wash it away immediately with large amounts of water and get immediate medical attention. The acid in the electrolyte can also ruin a car's finish or upholstery. If spilled, neutralize the acid with a solution of baking soda and water. Here are some important safety guidelines to use when testing or servicing a battery. Wear gloves to protect your hands when carrying batteries. Wear safety glasses at all times to avoid eye injuries. Remove rings and wristwatches. If they contact a live terminal, they'll melt on your finger or wrist and cause painful burns. Don't lay tools on the battery case or use power tools near the case. Both could cause dangerous sparks. Always disconnect the negative cable first and always connect the negative cable last. And when jump starting or charging a dead battery, follow the recommended service procedures. Besides safety, another important concern when checking or testing the battery on today's Toyotas is avoiding damage to the electronic systems and components. Disconnecting the battery will erase the memory on electronic devices, so retrieve any trouble codes before servicing the battery. Also, write down the settings for programmed components, such as radios. You should reset them after disconnecting and connecting the battery. And never disconnect the battery with the ignition on. Never use an electric welder without the battery ground cable disconnected. And never reverse the battery polarity. High voltage surges will damage electronic parts. Now that you're properly prepared, start checking for physical problems with a visual inspection. This may reveal simple problems that can be quickly corrected. It can also reveal problems that might require battery replacement. Check for cracks in the battery case. These could allow electrolyte to leak out. Check for broken or corroded terminals. These increase resistance to current flow. Also check for damaged cables or cable connections for the same reason. Then, too, check for a loose battery hold down. This could allow vibration that would shake active material off the plates. And check for dirt or moisture on the case top. This could allow current leakage and battery drain. You can also make a quick electrical check for battery drain using either an ammeter or a 12-volt test lamp. Do not use a voltmeter. The ammeter is connected in series between the battery negative terminal and ground cable. A reading of less than 1/2 amp is considered acceptable. Toyotas will typically show less than 1/10 of an amp. The other way is to connect a 12-volt test lamp between the battery positive terminal and its cable. The lamp should not light. If the ammeter reads more than 1/2 amp, or if the lamp lights, the cause of the battery drain should be located and corrected. No visual inspection is complete without a check of the electrolyte level. The level can be viewed through the case or by removing the vent caps and looking into each cell. If some cells have a low electrolyte level, add distilled water to those cells. Ordinary water may have dirt and other impurities which could affect the chemical reaction and damage the battery. Also, avoid overfilling the cells. The overflow could mix with dirt on the case, forming a conductive path for current leakage. And whenever water is added, charging the battery is a good idea. This will ensure that the water mixes with the electrolyte. Two other important checks should also be part of your visual inspection. Check the condition of the electrolyte, plates, and separators, and check the condition and tension of the alternator drive belt. Cloudy or discolored electrolyte could be caused by overcharging or vibration. If all the plates are light, severe undercharging is indicated. If the separators are cracked, the plates may be shorted. correct the cause of the problem and replace the battery. A loose drive belt will slip and prevent proper charging. A belt too tight will reduce alternator life. In either case, adjust the tension to specs using a belt tension gauge. And if the belt is frayed or glazed, replace it. If the battery's physical condition seems okay, there is no battery drain, and the electrolyte level is okay, you should check the battery's chemical condition or state of charge. The most accurate method is a specific gravity test using a hydrometer. Another is an open circuit voltage test using an accurate digital voltmeter. And for a general indication of the battery's condition, check the indicator eye if the battery has one, or check the headlamp brightness during starting. We'll go over each of these checks. The hydrometer checks the battery's state of charge by comparing the exact weight of the electrolyte to the exact weight of pure water. Full-strength electrolyte in a charged battery is heavier than diluted electrolyte in a discharged battery. The specific gravity of water is 1.000. The acid is 1.835 times heavier than water, so its specific gravity is 1.835. Since the electrolyte in a fully charged battery is about 36% acid and 64% water, the full-strength mixture has a specific gravity of about 1.270. To perform a state of charge test, insert the hydrometer tube into the electrolyte and draw electrolyte into the tube. Without removing the tube from the cell, bend down and read the indicator float with the fluid level at eye level. Also, check the temperature reading on the thermometer. Do this for each of the cells and carefully record your readings. A fully charged battery will have specific gravity readings of about 1.265. This drops to about 1.190 for a half-charged battery and to less than 1.120 for a fully discharged battery. If there's a difference of 50 points or more between certain cells, the battery should be replaced. Since these readings are based on the electrolyte being at 80 degrees Fahrenheit, you'll have to correct them for different electrolyte temperatures. Add 4 points, or 0.004, for each 10 degrees above 80 degrees. Subtract 4 points, or 0.004, for each 10 degrees below 80 degrees. This is necessary because electrolyte is lighter at high temperatures and heavier at low temperatures. Another way to check the battery's state of charge is to measure the open circuit voltage. If the battery has just been charged, turn on the headlamps for 1 full minute to remove any surface charge that might give a false reading. Then turn the headlamps off and connect an accurate digital voltmeter across the battery terminals. A fully charged battery will have an open circuit voltage of at least 12.6 volts. The reading would drop to below 12 volts for a dead battery. An accurate voltmeter is a must for this test to be valid. 2 other simple checks of battery condition can also be made. Toyota original equipment batteries have an indicator for electrolyte level and specific gravity. If the indicator shows red, the electrolyte level is low, or the battery is severely discharged. If some blue is showing, the level is okay and the battery is at least 25% charged. The other check involves turning on the headlamps and operating the starter. The lamps should dim slightly. If they dim excessively or flicker, the battery is weak or its connections or cables are faulty. Your next step involves checking the electrical condition of the battery. As mentioned earlier, this involves a heavy load test and, if necessary, a 3-minute charge test. During your hydrometer checks of each cell, if the specific gravity readings average at least 1.225 and there is less than a 50-point difference between each cell, you can then perform a heavy load test. The heavy load test measures the battery's capacity to produce enough power for starting as well as for ignition. Using a Sun VAT40 tester or similar equipment, follow the tester specs for proper tester preparation. The load leads are connected to the battery, and the clamp-on amps pickup is connected around either of these load leads. Then load the battery until the ammeter reads 1/2 the battery's CCA rating, or 3 times the battery's amp-hour rating. With the battery loaded for no more than 15 seconds, read the voltmeter. If it is 10 volts or higher, the battery is okay. If it is at least 9.6 volts, the battery is serviceable but requires further testing. If it is less than 9.6 volts, the battery is not okay or requires charging. In either case, the 3-minute charge test should be performed. The 3-minute charge test will help you determine if a battery is good, chargeable, or bad. To perform the test, you'll use a battery charger and the Sun VAT40 or a separate voltmeter. The test should only be performed on a battery that passes a visual inspection, but fails a heavy load or capacity test. First, connect the voltmeter leads, positive to positive, negative to negative. Then, connect a battery charger and set the charge rate as close to 40 amps as possible without exceeding 40 amps. Note the voltmeter reading after 3 minutes. If the reading is more than 15.5 volts at any time, the battery plates are sulfated. Replace the battery. If the reading is less than 15.5 volts, reduce the charge rate and slow charge the battery until it reaches full charge of about 12.6 volts. It can then be load tested again. If the battery fails the load test a second time, it should be replaced. That completes our look at battery diagnosis and testing, and you've learned a lot. You've learned about the causes of battery problems, the guidelines you should follow for personal safety and preventing damage to electronic components during battery testing, how to perform a thorough visual inspection of the battery, how to check the battery's state of charge using a hydrometer, as well as some quicker, though not as accurate means, and how to perform battery electrical tests. Now, we'll briefly cover battery service. Some tips on how to correct battery problems. Spilled electrolyte and dirt or corrosion can be easily cleaned from the battery case using a mixture of water and baking soda. And tough-to-remove corrosion can be cleaned from terminals and cable clamps using the wire brush tools designed for that purpose. Charging, as mentioned earlier, sends current into the battery to reverse the chemical reaction in the cells. Safety precautions include never connecting or disconnecting leads with the charger turned on. Also, check the battery temperature. Fast charging may create enough heat to warp the plates or even damage the case. Most Toyota batteries can be slow charged at 5 to 10 amps in 15 hours or less. Fast charging is at 20 to 50 amps for 1.5 to 4 hours. When jump-starting a dead battery with a booster battery, make your connections properly to avoid sparks. First, connect the 2 positive terminals. Then, connect one end of the jumper cable to the negative terminal of the booster battery. And connect the other end to a good ground away from the dead battery. This way, if a spark occurs, it won't be near the battery. And last, if the battery does require replacement, use a cable puller to remove terminal clamps. Unfasten the battery hold-down, lift the battery from its carrier with the proper tool, wash and paint corroded parts, replace any damaged parts of the hold-down, support tray, or cables, and select and install a battery of the proper size and capacity rating. In this program on the battery, we've looked at its function, its construction, its operation, its diagnosis and testing, and its service. With what you've learned here and some practical on-vehicle experience, you should be able to identify terms relating to battery construction and operation, conduct a thorough visual inspection of a battery, perform a state of charge test using a hydrometer, perform a heavy load test, perform a 3-minute charge test, and perform basic battery service. For now, keep in mind that the battery, fully charged, provides Toyota vehicles with the power to perform. It is the primary source of electricity for an increasingly sophisticated electrical system that is doing more and more to provide the exceptional levels of comfort, convenience, safety, and performance that our customers now expect from Toyota. This program should provide you with a good start toward building the necessary skills to properly diagnose battery problems and correct them.